Hello, fellow pedestrians. In this lecture, we're going to examine, like we said, something called the general linear first order differential equation, which is of the form y prime plus p of x, function of x, y, is equal to another function of x. Now, this has a standard solution that can be used every time a linear differential equation of first order is unidentified, and it's really easy to identify what a linear differential equation is. You'll go ahead and look at each term that is summed, and except this one, which is an exception. This is just a function of x, and it doesn't fall under our consumption. And each term should have at least one y, could be y or y of prime or y of, I don't know, 4 times differentiated, but we're only dealing with first order here. And it doesn't matter if its term is multiplied with a function of x, but it does need to be alone, meaning that you cannot have y prime squared. This is not a linear term. So the order of the primes and y itself should be alone. They should be of order 1. Okay. Now the solution to this equation, the general solution, is c of naught of x going to be, sorry, integral r of x over c naught of x dx, where c naught of x is e to the minus integral of px dx. So for each example, we are going to identify what px and rx is and use this solution here. Try to solve everything, right? Nice. Let's begin with a very simple example. Let's say we have y prime minus y is equal to e of x. Now, p of x is minus 1, and r of x is e to the x. So we can go ahead and find y naught, which is e to the minus p of x, which is minus 1, so plus dx. And this is just e to x plus s, so a constant, times e to the x. Hence, y of x is going to be c naught, which is this guy here, integral of r of x, which is e of x, over c e to the x dx. This and this cancelled. This also cancels, and it doesn't matter that it is inside the integral because they're just constant. So you have e of x times x plus a constant, right? And this is indeed the solution to this differential equation. Let's check another example. Let's say you have 1 plus x squared y prime plus 2xy is equal to 1. Now, this is not written in this form, so go ahead and make it look like this. So we divide with 1 plus x squared, so you have 2 of x over 1 plus x squared y is equal to 1 over 1 plus x squared. And now this guy here is your p of x, and this guy here is your r of x. So C naught of x is e to the minus p of x, which is 2x over 1 plus x squared dx, and this is um, minus, this is ln of 1 plus x squared, right, plus a constant, because if you differentiate this, you have 2 to the x over this guy at the denominator, which again written as a constant, a different constant again. Like we said, we have a lot of freedom when using this type of constants. This constant is not the same as this, but it doesn't really matter. And we have e to the ln of 1 plus x squared to do it analytically. So this whole term is going to cancel, so say over 1 plus x squared. And the solution is going to be C naught, which is this guy, integral of r of x, which is this, over this guy, dx. And this all will cancel, this also cancels, so 1 over 1 plus x squared, integral of 1, sorry, so x plus a. And this again is our solution. And to write it more neatly, we can write this the denominator, right? Now, another example. Let's say you have y prime plus y is equal to x. You can see that px is 1 and r of x is x. This is p of x, this is r of x. So y naught is e to the minus integral of px, so px, and this is e to the minus x plus a constant or a different constant, e to the minus x. So finally, c of y of x is going to be y naught, which is this guy, integral of r of x over y naught, e to the minus x dx. Right. This and this also cancels, and this is written as e to the minus x, integral of x, e to the x dx. And by using partial integration, this can be written as e to the minus x. Imagine this is written like this. So you have x e to the x minus the integral of e to the x and the differentiated x with respect to x, which is 1. So this is equal to this. This is called partial integration. So finally, this will give x minus, this is also e of x, and times this will only get you 1. So 1 plus and this constant comes from here, so it will be multiplied with e of x. And this is again the full solution. Now, let's take an example where we are given initial conditions, so we can identify and find what the constant is. Of course, for differential equations where you have when you have a first order differential equation, um, one initial solution is enough to be able to find the constant because you only have one solution when you have a first order differential equation. For a second order differential equation, you will have two constants, hence you're going to need two initial conditions to be able to identify what the constants are. So let's say we have an example where x plus 1 y prime is y minus y is equal to x squared plus 2 with initial condition that y of 1 is equal to minus 1. Now, again, divide with x plus 1 to get it in the form that we want, which is this. So, y prime minus 1 over x plus 1, y is equal to, is going to be x minus x plus 2. Not going to simplify for us, unfortunately. So, didn't really have to do that. I just leave it like this. X plus 1. Okay. So, p of x is going to be minus 1 over x plus 1, and r of x is going to be x squared plus 2x over x plus 1. Right. So psi naught is going to be e to the minus p of x, which is this, so plus dx over x plus 1. This is nothing more than the logarithm of x plus 1, so e to the ln of x plus 1, or just x plus 1. We also had the constant here, so it's going to be multiplied with a constant. So finally, it's going to be y naught, so say x plus 1, and the integral of rx, which is this guy here, over x plus 1, over the newfound solution, which is constant times x plus 1 dx. The constants always go away, and this is x plus 1 integral of x squared plus 2x over x plus 1 squared dx. Now, if you notice, this can be written as a perfect square by adding 1. So, it can be written in this form if you add 1. So, this is written as 1, and you now have to subtract what you added, which is 1 over x plus 1 squared dx. And finally, this is just x, and this is just plus 1 over 1 plus x, and a constant again, to keep forgetting. And this is written as x plus 1 times x plus a constant. So this multiplied by x plus 1 plus 1. And this is the solution. Now we're given that y of 1 is minus 1. So if we plug it here, minus 1 is going to be for x equals to 1. So this is going to be 2 times 1 plus constant plus 1, or 1 plus constant. This is minus 2 over 2 minus 1. So the constant is just minus 2. And the full solution, differential equation for the given initial condition, is x plus 1 times it was x plus z, so x minus 2 plus 1. Let's take one last example and get it over with. Now, y prime plus tangent of x minus 1, y is equal to minus cosine of x. Now, again, this is r of p of x, sorry, and this is r of x. So, y naught is e to the minus p of x, which is tangent of x minus 1 dx. And to find this integral, the tangent of x dx is written as sine of x over cos of x dx. Now we can make transformation of this kind and, let's say, change a variable, and u is equal to cosine of x, then du is going to be minus sine of x dx. And this integral is now going to be written, this is minus du over u, which is nothing more than minus, this is ln of u, and u is called cos of x. So we know what this is. Let's put this like this. Now if we return here, this can be written as minus what you found, so e to ln cos of x, and this was going to be plus x plus a constant. It's going to give us a constant times e of x times this guy here, which is cosine of x. So finally, y of x is going to be y naught, the e of x cosine of x, integral of rx, which is this guy here, minus cos of x, and this is y naught. So e a to the x cosine of x. Things simplify a lot. This and this goes away. So and this also cancels. So minus e to the x cosine of x, and you have just the integral of e to the minus x dx, right? Which is nothing more than the same integral with a minus sign. So e of x cos of x e to the minus x plus a constant. Don't forget this. This is nothing more than cosine of x. Get this guy inside, so 1 plus a constant e of x. And that's pretty much it. I mean, once you identify a linear differential equation, you can go ahead and use these solutions and be able to find right away what you're dealing with and have it your way. Now, for the next lecture, we are going to try to tackle something called exact d's, which will be of the form p of x and y dx plus q of x and y dy. And we'll see that this is very useful in times where all other tricks that we have upon our sleeve won't be useful, which they are going to also give us a lot of solutions to be able to work with. So thank you all for watching, and I will see you soon on the next lecture of this series. Thank you all.